Welcome back to another lecture on this advanced plasticity on solid continuum. Today we will be discussing on the isotropic and kinematic hardening, the two major hardening phenomena that typically define the different hardening scenarios that one comes across in experiments. So we will take a look at the physical insight as to why these hardening phenomena are important. And also we will consider the thermodynamic structure which are engendered by the introduction of this kind of hardening in an otherwise perfect plasticity model. So let us get going. So as I said, from perfect plasticity we have to move on to plasticity with hardening. You would recall that perfect plasticity has a fixed yield surface. So there is no dynamics for the yield surface. This is not what is experimentally evidenced if you do experiments on metals or other materials like polymers. You will see some dynamics of the yield surface as the loading continues or the loading is discontinued. The yield surface will be moving. So we can actually identify two different aspects of this motion. One is an expansion of this yield surface. You know that yield surface is a closed set in the stress space, right? In the space of all stresses, the yield surface is convex and closed, right? So we can think of it like a ball, right, in the stress space. So when I say it expands, it is like the ball increases in volume, right? Or it may so happen that it moves. In other words, by taking the analogy of that ball, the center of the ball starts translating in that case. So typically what we see in experiments is a combination of both these phenomena, right? So basically the experiments, as we have said here, show stress increases after the yield, right? So basically first time if you just load a body, right, then this is my stress. I mean, this is done in a very schematic manner because stress is not a line but a tensor. All right, this is some strain. Think of it purely schematically. So this is the elastic curve. This is the initial yield point from which we have a hardening like thing. Okay, and then if you unload from here, from the next time you have to unload from here, right? And the next time you come back, the yield point would have changed from here to here, up. Okay. So you see that essentially that is the dynamics that we are talking of. That is part of the dynamics that we are talking of. So the yield stress typically increases, right, after the yield. Now the yield surface has a dynamic structure, as we have said. Of course it is history dependent because plasticity by its very nature is history dependent. By history I mean the history of the response. Now the hardening, as with all forms of different phenomena associated with plasticity, hardening also reflects certain aspects of the microstructural evolution. But one thing that has to be remembered here is that the hardening is not just dissipation. It is some kind of an energy storage, right? So the difference between the energy storage and dissipation is that the energy storage is not seen. Even if you wait for a very long time, it is not seen as heating of the body. Dissipation ultimately results in plastic heating, right? So that is a major difference that you can actually cross check through an experiment, which is energy storage, which is heating, etc. Let us take a quick look at the microstructural origin of hardening, all right? As we already know that there are multiple mechanisms, including the Frank-Reed mechanism that we talked of some time back, by which plastic deformation would increase or multiply the dislocations, right? So it will increase the dislocation density. And the more there are dislocations, the less will be the chances of other dislocations to or including those dislocations which are in the forest of dislocations to move, right. In the process, what actually can happen is that long range stresses can develop. It is not just the dislocation increase in density of the dislocation that is of importance in impeding the motion of dislocations, but also the dislocation motion can be impeded by the presence of certain inclusions or voids or the presence of grain boundaries. So therefore, if the dislocations find it difficult to move, then higher stresses will be needed for continued plastic flow, right. So that is what basically is manifested in the macroscopic hardening phenomena that we just drew in the last slide. So the evolved microstructural orientation also may induce asymmetry between the forward loading and backward loading paths. By that what I mean is that this is called the Bauschinger effect. Probably I will come to this later on, but this is an orientational effect. That means the loading may orient the microstructure in such a way that if you now reverse that loading, then the orientation has all that previous orientation has already created some internal stresses, something like a residual stress. So the reversed loading, now we have to overcome that extra stress, right. So that is the orientation dependence, which is basically manifested in what we call kinematic hardening, right. So so therefore there are two issues here. One is that the plastic the yield surface can just expand, which is basically manifested in what we call isotropic hardening, or it can actually its center can move, which is kinematic hardening. So these are the two things you need to remember. Now let us take a look at the plastic work and the storage versus dissipation aspect, that is which part is stored, which part is dissipated. So we know that the plastic work is given by the stress times the plastic strain rate, but we know that if plasticity is really nearly incompressible, then the stress sigma has to be replaced by its deviatory counterpart, right, deviatory component. But even though this is the plastic power, not all of this plastic power really is dissipated into heating finally, okay. Part of that can be stored as the hardening energy, which is never manifested in heating. But that does not mean that by removing the loading you really recover this hardening energy. It is not something like an elastic energy. It is in principle, yes, but to produce an experimental mechanism in practice to recover this will be very difficult. So this is also non-recoverable energy, but this is actually stored energy, right. So just for the sake of mathematical convenience, you can think of this as recoverable, but in practice it is not. So as I said that the hardening could be kinematic or isotropic. Isotropic hardening means uniform extension of that so called ball, which is a schematic representation of the yield surface, which is a closed surface in the stress space, and kinematic hardening would imply a translation of the center of that ball. So let us discuss isotropic hardening first, where the yield surface isotropically expands about the origin. By origin I mean the zero stress point in the stress space, okay, the zero stress tensor point. Every element in the stress space is a tensor, right. So when I say zero element in the stress space, I mean the zero tensor, okay, or zero matrix, right. Now let us first consider the small strain case of plasticity, as we have been doing, because that completely does away with the worry of multiple configurations. So the deformations involve small strain, Recall that this additive decomposition is always valid for such cases, that is, the total strain is split into the elastic and plastic parts. Epsilon E is the elastic part, epsilon P is the plastic part, alright. Now the internal or the isotropic hardening variable, let us call it by alpha, okay. So this alpha is excluding already one internal variable, which is this epsilon P, which is the plastic strain. This is also an internal variable. Ideally I should include this within alpha, but let us consider from now onwards alpha as representing only the hardening variables, okay, the extra ones. Now if you take the rate of this last equation, this additive decomposition of strain, then we directly get this straightforwardly. We get this epsilon dot equals epsilon E dot and added with epsilon P dot, right. So dot means derivative with respect to time. Now let us first talk about the thermodynamic aspects of this now. We are now ready to do that. So first let us understand, as we have been saying, that hardening in principle contributes to the energy that can be recovered. It is a stored energy in principle only. So it must be included therefore as an argument of the free energy psi. Earlier in one of the lectures I said that psi cannot be a function of epsilon P in the context of perfect plasticity. That is because in perfect plasticity there is no storage of energy, the whole thing is dissipated and finally manifested in heating, right. But in this case alpha is not like that. So therefore psi, I should consider this to be a function of the elastic part of the strain and the hardening variable alpha, right, and then split this free energy into two parts. I mean, this is an added approximation for simplicity of further considerations, the mathematical considerations, that psi has an additive decomposition in terms of an elastic part psi E, which is only a function of the elastic strain, small strain, and a hardening part psi H, which is only a function of the hardening variable alpha. So as I have been repeatedly emphasizing, that psi H represents the stored hardening energy. Something that is stored is never really dissipated in heating, okay. Now let us define, so we have been talking about we have actually finished introducing you to the Coleman-Knoll procedure, which is a systematic means of imposing the two laws of thermodynamics as part of your formulation of the continuum plasticity, right. So therefore if we invoke the Coleman-Knoll, we already saw in the context of let us say both thermoelasticity, in the special case of elasticity as well as in plasticity with perfect plasticity of course, we saw that sigma is basically the partial derivative of the free energy with respect to the elastic strain del psi by del epsilon E. You should remember that. Now let us define this variable, which is called the hardening. This is the force, the thermodynamic hardening force conjugate to this hardening variable alpha. Think of alpha to a counterpart of epsilon E, both are kinematic. It is something to do with the straining of the body, right, something, even if it is remote, the connection may be remote, but still it is. So the differentiation of psi with respect to that sort of a kinematic variable produces something like a force, a generalized form of a force, right. So this xh is henceforth called the hardening force, all right. Now assume no heat transfer for the time being, all right. Why? Because after all I know that there is the perfect plasticity part here too, right. So hardening plasticity means there is a perfect plasticity part plus hardening is an additional mechanism, and we know that perfect plasticity always dissipates heat. But remember one thing, that when actually the dissipation occurs, its manifestation as temperature change takes some time, right. If your experiment is finished before there is the scope for the material body to change its temperature because of this heat dissipation, then you won't see that increase in temperature. So we are talking of time frames in which this heat transfer is not taking place. That means your experiments are fast enough. It is not waiting, these experiments will not wait for that long for the heat to transfer and manifest as temperature changes. Okay? So we can therefore think of this whole problem as an isothermal problem, no temperature change. All right. Now in that case, from a purely mechanical perspective, this is my dissipation inequality. This is the mechanical dissipation inequality, which states that this is the stress power and this is the psi dot. So stress power minus psi dot must be greater than or equal to 0. Now we have already seen how to derive this sigma equal to del psi by del epsilon by Coleman-Knoll. You can actually do this here too, you know. So to do that, what you can actually do first, you can split this epsilon dot into epsilon E dot plus epsilon P dot, right. And then psi dot you will have to write as you have to expand psi dot, right. Expand psi. So psi is basically a function of psi of epsilon E and alpha, correct. So psi dot will be your del psi by del epsilon E dot with a colon here because these are matrix multiplications, plus del psi by del epsilon E, sorry, this is so this is basically, I will rewrite rather than removing it, del psi by del alpha dot, correct. So assume that alpha is currently a scalar variable, right. So that you just multiply del psi by del alpha with alpha dot. Now if you do that and put this into this expression for psi dot here, and then apply the Coleman-Knoll procedure, factor them out properly, then what you will lead to, I would ask you to actually do this. I have not, you know, done it step by step here because I have left it for you to actually come to this step from here to here, okay, by putting this expression for psi dot, right, and applying the Coleman-Knoll and requiring that epsilon E dot can be independently specified locally with respect to epsilon E, right. So all that, so you will be getting this reduced dissipation inequality, right, which is basically sigma 0, the deviatoric counterpart, the deviatoric part of sigma times epsilon P dot minus xh times alpha dot, right. Now you see that this is the actual dissipation which was there in the perfect plasticity. From there, because of the introduction of hardening, this part is removed, which is expected because this part is stored, right. So therefore I can say the hardening reduces net dissipation, right. So because of this incompressibility, recall that we are only interested in the deviatoric part of sigma, right. So only sigma 0 can produce power by being applied on epsilon P dot. Now let us come to the specific cases of hardening, some examples of hardening, right. So let us consider the linear isotropic hardening. So in this particular case, you remember that psi was split into psi E of epsilon E and psi H of alpha, right. So this psi H of alpha, let us take it to be of this form, half of H times alpha squared. This H is the hardening modulus, let us say it is greater than 0, all right. It is called the hardening modulus. Now because the energy here, the hardening energy is a quadratic function of alpha, you can expect therefore, because an xh is basically the derivative of psi h with respect to alpha, therefore you can expect this to be the linear type of hardening, right, because any quadratic energy leads to a linear problem. Now so XH in this particular case will be simply H alpha if you differentiate, right. XH, as we have already seen, is called a thermodynamic force arising out of hardening. This is the typical scenario actually what is happening. So, you can see for yourself that schematically this is, let us say, stress direction A, right, and this is stress direction B here, right, and you know this is the initial yield surface in blue, and it expands isotropically uniform in all direction about the origin in the stress space, right. This is the schematic. So, this is how it expands. Now, you know, how does it expand exactly? To see that, you can actually reconstruct now in this particular case the yield function. The yield function now, the yield surface will be defined by f equal to 0, of course, the yield surface, right. Now, the yield surface is f equal to 0. What is the function f? It is the norm of the deviatoric stress minus now sigma y plus h alpha, that is that xh. So, sigma y is added to by xh, the hardening force, right, and yield surface therefore, because if alpha increases now, right, now we will actually evolve, we will have to evolve alpha. If we see based on that evolution that if alpha increases in time as plastic flow continues, then h alpha will increase. So, sigma y plus h alpha will increase. So, therefore, actually it will go on blowing up, the ball will go on blowing up indefinitely, right, whilst preserving the convexity, of course, right. This increase in the size of the ball, that is the yield set, is essentially radial as alpha increases. But such an isotropic expansion cannot really happen indefinitely, impossible, right, because if it goes on taking, you know, more and more stress like that, if the yield stress goes on increasing, then the material can, you know, resist anything, which is not the case. Actually, sometime afterwards the damage would take over, that is another mechanism different from plasticity, and therefore this process will stop, but we are not considering that, including that in this model, right. But one way of including that, not damage directly, but one way of restricting this indefinite increase in this swelling up of this yield surface is to use nonlinear isotropic hardening. What we do here, we define the psi h as a function of alpha, what is shown here. Okay, so, integral 0 to alpha, that variable alpha itself comes as part of the limit of this integral rs ds. So, you can understand, since the limits are from 0 to alpha, since the limits are over the, you know, the hardening variable itself, so this s is a dummy for the hardening variable, right. So, alpha is r is a function of the hardening variable, right. So, if you differentiate this with respect to alpha, right, you will be getting nothing but xh equal to r alpha, the alpha that happens at the top of this limit, the upper limit, right. So, r alpha controls the hardening rate, right, and so xh is also r alpha here. Now, we have to actually construct a form for r alpha. This is a specific form which is called the saturation hardening, where r alpha is given here. Q is a factor, is a scalar positive number, 1 minus exponential minus b alpha. B is also another material parameter greater than 0, right. So, you can understand actually what happens now. If alpha increases indefinitely, then e to the power minus b alpha tends to become e to the power minus infinity, which is 0. So, therefore, it reduces to q, r alpha reduces to q. So, basically this modified yield stress, because of this isotropic hardening, saturates at sigma y plus q as alpha becomes large, right. So, this models the saturation effects. This is a more realistic isotropic hardening model. Now we come to an important part, which is the evolution of the hardening variable. We have not yet told you that, right. One standard and the simplest way of this evolution is to relate the hardening variable to the plastic strain itself, right, and require that alpha dot is the norm of the plastic strain rate. Okay. This relationship is not trivial, it is not an algebraic relation, because of the simple fact that if you integrate this, you have to integrate. So basically alpha becomes integral over 0 to t, alpha at time t will be 0 to t norm of epsilon p dot, okay, as a function of, let us say, s is less than or equal to t ds, right. So basically what is happening, alpha is history dependent, right. So the expression is not algebraic, the relationship is not algebraic, so it is quite non-trivial. But the alpha therefore measures the accumulated plastic strain, correct, and it ensures, of course, that if you evaluate this integral, it can never be less than 0, right. So therefore alpha is always greater than or equal to 0. Now, which also means that the isotropic hardening will ensure that the yield surface goes on expanding. Now let us define the set of admissible stresses, right. Earlier in perfect plasticity, it was only given by a spherical surface of radius sigma y, correct. But in this particular case, you know, because of this hardening, sigma y changes, right, isotropically, as the isotropic hardening takes control. So C alpha, C will be a function, the set C will be a function of alpha, the hardening variable. It is defined by the set of all hardening the stresses, not the set of all deviatoric stresses sigma 0, such that the norm of the deviatoric stress is less than or equal to sigma y plus r alpha, and this r alpha is nothing but xh. So I can say this is sigma y plus xh, the hardening force. So this is still convex, this is still closed, no problem, but it expands isotropically and the shape is unchanged. So basically, so this is the situation for the isotropic hardening. We will be taking a look at the dissipation structure after we take a quick breather. So we will come back after a short breather. Thank you very much for your attention.